So what we're looking at here is a video titled, Does the Earth Rotate? Let's have a look by Bob the Science Guy. And I'll play the video in full shortly with Bob's permission. Many flat earthers, in addition to believing the Earth is flat, also claim that it is motionless, that it does not move. And in this video, Bob looks at several ways that we can confirm that the Earth actually is moving. If you haven't seen Bob's channel yet, please check it out. The quality of his work just keeps getting better and better, and his style is both entertaining and educational at the same time. So as you can see, I'm subscribed to Bob, and I also have the bell notification active, and he's one of the few channels that I've done that with because of the quality of his work. Please head over, check out the channel, you won't be disappointed. So without taking anything away from Bob's video, I just want to talk on this topic myself, because one of the areas that flat earthers like to focus on are gyroscopes. And this is a very famous flat earth video where Rob Durham uses an aviation directional gyro to demonstrate what he believes is a stationary Earth. Now, Rob's a pretty decent guy, so please don't go over and give him a hard time. I did have some conversations with him several years ago when he first produced this video. He made a number of mistakes, and the first one was he was powering the gyroscope with compressed air. Now, this instrument is designed to be operated with a light vacuum, so that was one of the mistakes. And the other mistake he made was not realizing that these gyroscopes are in fact calibrated for a specific latitude. Let's take a look at that now. So I'm going to show you exactly how these gyroscopes are calibrated for latitude by referencing the exact service letter for the Sigmatek gyroscope that Rob used in his video. And you can find that on the Sigmatek website under technical information, and then go down to service bulletins, and it's this one here, 100L039. We'll look at that shortly. Firstly, I want to show you a document on the Civil Aviation Safety Authority website, and I'll post the link to this document in the description below. It's a PDF document, and it's an airworthiness bulletin talking about gyroscopic instrument reliability. It's a good read. It shows the basic concept of how they work, but very specifically, we're going to go down to paragraph 3.6, and I'll read it through for you in its entirety. Directional gyro heading drift latitude compensation. Due to the rotation of the Earth and the orientation of the directional gyro DG spin axis, all directional reference gyros will want to drift from the heading set by the pilot during the flight. The rate of apparent drift will vary according to the latitude at which the aircraft operates. Some directional gyro designs will have automatic latitude compensation when linked, slaved electronically in a magnetic compass system, and or have a means to allow the pilot to apply latitude correction to compensate for gyro heading drift. Basic directional gyros, however, require the pilot to cage the gyro and manually reset the heading every few minutes during flight. The frequency at which the gyro has to be reset depends on factors such as gyro imbalance, bearing wear, internal gimbal friction, and the accuracy of the internal compensation or latitude correction for the particular geographic location. The maximum gyro drift error is considered to be approximately 4 degrees per 15 minutes. Drift compensation or latitude calibration for a basic directional gyro is usually set at overhaul. When sending a directional gyro overseas for overhaul, be aware of the Earth hemisphere to which the gyro is being sent and which Earth hemisphere it is intended to be operating. Some gyro overhaul facilities based in the Northern Hemisphere receiving a DG from Australia recognize that the gyro will be operating in the Southern Hemisphere and will automatically provide Southern correction, specifying Southern correction on the purchase order for an overhaul of a DG intended for installation in an aircraft operating in Australia should ensure an acceptable latitude correction calibration is applied. So this is the service letter on the Sigmatek website for directional gyro recalibration for the Southern Hemisphere. And remember, this is the same directional gyro used by Rob Durham in his video. The purpose of this service letter is to explain the recalibration of the Sigmatek directional gyro for use in the Southern Hemisphere. It talks about the test procedure, which is called a Scoresby test, and that is to mount the instrument on a Scoresby table set for 3 degrees oscillation in pitch, roll and yaw at 5 to 7 oscillations per minute. Start the instrument and run for 10 minutes using 5 inches of mercury vacuum. And remember, Rob powered his with compressed air. It's designed to operate from vacuum. Set the heading dial to 0 degrees, then start the Scoresby motion. After 10 minutes, stop the table oscillations, return it to starting position and note instrument indication. Maximum drift must not exceed 4 degrees. Repeat the test at 90, 180 and 270 degrees. If the unit passed the above test, no recalibration is required. If the unit does not pass, move to step 2. Now step 2 requires the technician to disassemble the gyroscope and adjust the calibration screw. You can see there in figure 3. Step 5, adjust the calibration screw as shown in figure 3. There's the calibration screw, and what that does is cause the gyro to have a slight imbalance that will induce a precession that is opposite to the rotation of the Earth. By setting it correctly, it will in fact counteract the rotation of the Earth, and therefore when you're doing a test like this, it is absolutely invalid to determine the motion of the Earth, because Rob did not know that this gyroscope has an internal calibration, and he did not know for which latitude it was calibrated. So the real question is, why do they need these calibration screws? Why do they need to be adjusted for latitude if the Earth was motionless? And why does the calibration have to be different in the Northern Hemisphere versus the Southern Hemisphere? All good questions for flat earthers, which they obviously cannot answer. So I'll now play Bob's video, and you can watch it all on my channel, but better still, why not head over to Bob's channel and watch the original directly there. I'll post a link in the description below and also in a pinned comment. Head over and visit Bob. I'm sure he'll give you a very warm welcome.
Well, hi everyone, and greetings from Northern Michigan. This is Bob the Science Guy. You know, one of the things that really interests me about the Flat Earth movement is some of the questions that they ask, because they make me start to think back to my middle school, high school, and college education. One of these questions is, well, I can't feel the Earth moving under me. How can you prove to me that it's rotating? Now, I obviously like the rotating Earth. It's in the background right here, sped up over 700 times. So when Ranty Flat Earth and I spoke about appearing on his new series, he asked me to come up with a good idea for a video that I could present, and I decided to go ahead and show the demonstrations of how we can tell the Earth is rotating. So I hope you enjoy it. The first thing that I thought I would talk about would be sunrise and sunset, dusk and dawn. What evidence does this give us that we are on a rotating spherical Earth versus a flat stationary Earth with the sun moving overhead? Now let's start off with this photograph right here. This is we'll say it's a sunset. There's a couple of things that you can note with this. First, we're looking out over water. Second of all, the sun is halfway under the horizon. And third, the bottoms of the clouds are lit up. Now, demonstrating the exact same principle is this shot of Mount Rainier in Washington State in the United States. You can clearly see where the sun is in the mid portion of the photograph on the left. Mount Rainier is casting a shadow upward onto the base of the clouds above it, and of course the clouds are lit from the underside as well. Now, one thing that you will occasionally hear in the flat earth community about photographs like this is that this is merely the sun reflecting off of the surface. Well, in the first example, the sun would be reflecting off of water. In the second example, the sun is reflecting off of tree-covered hills. Obviously, the reflective index of water, snow and ice, tree-covered hills is different, yet we see the exact same effect. This is direct sunlight shining through the mountain and casting a shadow on the clouds, and it's direct sunlight illuminating the bottom sides of clouds. Now, another term that you will hear bandied about occasionally is perspective. This photograph is an excellent example of perspective. Here we have two stairways that have partial walls on either side of them, and then we have a brick space, and above that is a roof. If you were to imagine the sun being suspended from that roof and the clouds being at the top of those half walls, you can clearly see that at no time, due to perspective, would the sun ever appear to be below the clouds. So it's simply not a tenable excuse. Now, on a flat plane Earth, there is no conceivable way that the sun can appear above the clouds at noon, yet below the clouds at dawn and dusk, without multiple violations of geometry and perspective. However, it is easily explained on a curved Earth, whereas the sun, represented by the blue arrow, illuminates the bottom side of a cloud after sunset that is observed by someone in the dark side of the Earth looking upward in the direction of the red arrow towards the bottom of the clouds. So this mandates a curved surface of the Earth in the east-west direction, and either the Earth is rotating under a fixed sun, or the sun is following a circular orbit around a stationary but curved Earth. The pattern of light and shadows at sunrise and sunset confirms that the Earth is curved in the east-west direction, and it rotates relative to the sky. Now let's turn our attention to the heavens and address the matter of star trails, domes, and spheres. Now this is a panoramic photograph of the 24-hour sun at one of the poles. You can see where it dips down towards the horizon represents sunset and sunrise, and then as it reaches the highest point of that roller coaster, that would be noon. They are 12 hours apart. Now our observations of the sun in the east and west directions suggested a curved surface of the Earth which was rotating relative to the position of the sun above it. Let's turn our attention 90 degrees to the north and have a look at the northern celestial pole. This is a shot from the northern hemisphere. You can see the star trails are rotating in a counterclockwise manner around Polaris, which is at the center of the circle there and is stationary. This could work on a flat, round Earth that was rotating about the North Star. However, we do have a problem. And that problem is the southern celestial pole, which is seen here. Notice that the star trails are moving in a clockwise direction, opposite what we see in the northern hemisphere, rotating about an empty space called Cygnus Octaris, which is the southern celestial pole. There is no rotational geometry that will allow a rotating flat Earth to create both a northern and a southern celestial pole. The fact that there is a north and a south celestial pole with the stars rotating around it, and that we cannot see Polaris from the southern hemisphere